Hello everyone. Here we want to study about how to improve SNR and how to reduce intersymbol interference. When we are doing the transmission and we will get the data at the baseband receiver. At that time we are supposed to improve SNR. So here we can see noise is nothing but it is the important area, because here we are supposed to study the baseband receiver according to the accuracy point of view. So we can say from the accuracy point of view, noise is the important concern, and here we are saying that noise is nothing but AWGN, additive white Gaussian noise. So we can say here that noise is the AWGN, which will have the power spectral density, the integrate and dump type filter process, the noise power spectral density, and which will give the output power spectral density GNO of F at the receiver. So we can consider the transfer function of that filter, and you will get the relationship between which we are sending at the transmitter and which we will get at the receiver. So you will get here GNO of F equal to Gn of F modulus Hn of F square. So we can say here RMS noise power we are taking as N0. So we will get that as N0 equal to the sigma 0 square, sigma naught square. We are saying that as the variance. So we can see here the input and output noise power spectral density relations, how they are related. So input we are taking as Gn of F, output we will get as a GNO of F. So we can say we will get GNO of F equal to Gn of F into in modulus Hn of F square. So we can say for the integration in the block H of F, we can replace integration by 1 by s. So here when we are doing the transmission and we are replacing integration by 1 by s in the frequency domain. So if we are taking the gain of system as a unity for the integrations, you will get the transfer function as we are taking here transfer function. So you will get as 1 by s. 1 by s we can take as 1 upon j omega, but omega we can write 2 pi f. So we can write 1 upon j 2 pi f. So you can say for the delay you will get, if x of t is Fourier transform, we are taking as x of f. Then you will get x of t minus t0 ka Fourier transform, you will get e to the power minus j omega t naught into x of f. For that you are supposed to understand how we are taking its Fourier transform. These concepts you will get in digital communication, in the digital signal processing, and you have seen in the signal and system also. So you will need it here how we are taking the transfer functions, how we are taking the Fourier transform. So if we will combine above equation 3.6 and 3.7, you will get here the time constant term. We are taking that as nothing but a time delay, tau. So we can say if we are taking the tau for constant forward path gain factor, we will get the transfer function for integrate and the dump type filter we are taking as, you will get h of f equal to 1 upon j omega tau into 1 minus e to the power minus j omega t. So here you can say when we are calculating the output noise power, we are taking that as a N0. So you will get that as integration minus infinite to infinite. Output is nothing but we are taking as GNO. So you will get GNO of F df. So you can solve that equations. So you will get not neta is nothing but efficiency, neta into t upon 2 tau square, time constant. So here we can see about the figure of merit and the probability of error. How we are taking, how we are supposed to increase the SNR, how we are improving the SNR. So here you can see the signal power and the noise power of detected signal can be derived as, you will get noise power, you will get neta t upon 2t square, which we have just seen. And here you will get signal power, that is nothing but P of S. You will get Vt upon tau square. So we can say the figure of merit is nothing but, it is the ratio of signal to noise ratio. We are saying the figure of merit as a SNR. So you will get as PS upon PN, signal power upon noise power. Signal power we are taking Vt upon tau square. Noise power we are taking as neta t upon 2 tau square. If you solve, you will get 2v square t upon neta. Because tau will get cancelled, that is tau square is in numerator and it is as well as in denominator. Now we are supposed to study about the probability of error. So here the probability density of noise sample is a Gaussian. So we can see here, if we are taking here the symbol, if we are taking here the signal, at that time we are supposed to see the probability density of a noise sample. We are taking noise sample, we are denoting by N naught t. So we can say we are supposed to take the probability density of the noise sample N naught t is a Gaussian. So we can see here, you will get its probability of error, that is equal to integration minus Vt by tau to infinite f of N naught t d N naught t. So if you solve, you will get that as 1 by 2 into ER Fc into Es upon neta raised to 1 by 2. So you can say at the end of bit interval, when we will get S naught t equal to Vt by tau for logic 1, error will occur. And if N naught t, that will be less than minus Vt upon tau. So we can say the probability of, in this case, is given by mark area. You can see here in the figure 3.9. Because of the symmetry of Gaussian curve, both curve marks 0 and 1 are of equal area. And so probability of error is sufficient to deduce the entire error probability. Now here we are supposed to study about the optimum filter. So what here we are saying, the integrate and dump circuit will emphasize the signal output in comparison with the noise voltage. So here we have seen error probability, that is dependent on the, we have just seen the error probability. You can see here. What we have seen, it is depend on Es upon neta. If you see, Es upon neta.